Okay, so in this video, I want to just run over the permanganate and iron titrations. So remember our primary standard for acid-base titrations was anhydrous sodium carbonate, but the primary standard for redox titrations is ammonium iron 2 sulfate. You must have the two written like that in Roman numerals. You cannot have the number 2, so be careful with that. Now, what do we know about a primary standard? So if I tell you that ammonium iron 2 sulfate is the primary standard for these titrations, then you know that it's stable, it's pure, it's soluble, 3 S's, and it's a solid. And we can dissolve it in a certain volume of water, a certain mass of it, and then you know the concentration precisely. So we can make up the primary standard into a standard solution. Now, the only thing is, there's a little difference in the procedure. When you're preparing a standard solution using ammonium iron 2 sulfate, you must add a little bit of dilute sulfuric acid. You must know the reason for that. And the reason for that is to prevent the oxidation of Fe plus 2 to Fe plus 3. Now, what would oxidize Fe plus 2 ions? Well, oxygen in the air or oxygen in the water. The secondary reason then is to prevent hydrolysis, okay? So you mustn't mix up the additions of sulfuric acid. So this is when you're making up your standard solution. So you would weigh out your 9.8 grams of ammonium iron 2 sulfate in a clock glass, add to a beaker of deionized water, but that deionized water in the beaker contains sulfuric acid, and you need the reasons for the sulfuric acid. To prevent oxidation of Fe plus 2 to Fe plus 3 by oxygen in the air or oxygen in the water. And the secondary reason is to stop or prevent hydrolysis. Hydrolysis means the substance that you're putting into the water is reacting with the water. You do not want that. Now, iron Fe plus 2 is being oxidized to Fe plus 3 because it's going to increase there in oxidation number. So that's oxidation. And remember, the substance that's being oxidized is the reducing agent. It's bringing about reduction in something else, okay, because it's losing an electron, allowing something else to gain that electron, okay? Now, on the other side then, remember now, if you're going to have iron being oxidized, you need something to be reduced. So it's the permanganate that's the oxidizing agent. So look, KMnO4, it's not a primary standard. Why not? Because it's not soluble. Remember, I had to heat the water to get the KMnO4 to dissolve in it, and it's also not stable. It decomposes in sunlight. So KMnO4, not a primary standard. So how will we calculate the concentration of a KMnO4 solution? We have to titrate it with ammonium iron 2 sulfate. So the whole point of the first titration is to standardize the KMnO4 so we can use it in subsequent titrations. The Mn plus 7 is purple. That's going to be reduced. Look at the numbers. Plus 7 down to plus 2. A decrease in oxidation number is reduction. So the KMnO4 is acting as an oxidizing agent. It's being reduced itself. It doesn't need an indicator. It acts as its own indicator because look, Km plus 7 is purple and Mn plus 2 is colourless. And lads, the other thing to be mindful about with KMnO4 is that you read the top of the meniscus because it's so darkly coloured you can't actually see the bottom. The KMnO4 went into the burette, and 25 cubic centimetres of your iron solution, your standard solution, was pipetted into your conical flask. Now, look, I've H2SO4 here again. The reason for the second addition of H2SO4, it's an acid, so it's going to supply H plus ions, as all acids do. What's the reason for the H plus ions? To fully reduce the MnO4 minus to Mn plus 2. So when you're reducing the MnO4 minus, it means the hydrogen ions will take away the oxygen, take away the 4 oxygen atoms there, leaving you with just Mn plus 2. If you added insufficient acid there, then what you'd observe would be the brown precipitate of Mn plus 4, not enough acid to fully reduce the MnO4 minus from plus 7 to plus 2. So you're getting plus 7 down to plus 4. So you'll observe that brown precipitate of MnO2 or Mn plus 4 if you don't add sufficient acid. And the other thing to say about the acid is, if they said to you, could you use HCl? No, you can't use HCl because the Cl minus ions will be oxidized and you'll produce chlorine gas, so you'll poison yourself. And you cannot use nitric either because nitric acid is also an oxidizing agent, okay? And if you use nitric, you'd be introducing a second oxidizing agent, if you like, and you would interfere with the results. Your result would be inaccurate as the result, okay? So that's kind of the theory behind the titration. Now, for the purpose of the calculation, I'm using 2009, okay? So you need to look up 2009 question 1 so that you'll have the details. But essentially there, I might just run through the theory questions as well as I'm at it. So the first thing said, why are iron tablets sometimes medically prescribed? Doctors will prescribe iron tablets to treat anemia. If you're anemic, you don't have enough iron in your diet, and therefore you'll take iron tablets. Iron tablets are FeSO4. So you would see, if you read the packet on an iron tablet, ingredients, whatever, it's FeSO4. So they're a source, if you like, of Fe plus 2 ions. There are Fe plus 2 ions in the iron tablet. FeSO4 is not a primary standard. So you can't dissolve iron tablets because it's not stable, by the way. So you can't dissolve iron tablets and, make up the solution, make up a primary, make up a standard solution, sorry. So how will we calculate the concentration of iron in iron tablets? Well, how we do that is we titrate against a previously standardized KMNO4. What does standardized KMNO4 mean? The first titration that we did in the redox chapter was we titrated KMNO4 against the standard solution of ammonium iron 2 sulfate to get the concentration of the KMNO4, to standardize the concentration of, or the solution of KMNO4. So we're going to use the standardized KMNO4 against an iron tablet solution. Now, in this particular question, they said that they had 5 tablets, okay? So 5 tablets, other information that they gave you, and they dissolved the 5 tablets in 250 cubic centimetres of deionized water. There was a little bit of sulfuric acid added to that water when they were dissolving the tablets. And in part C of the question, they asked you the procedure for doing that, and they asked you to explain the reason for the sulfuric acid. So when you're making up your iron tablet solution, you crush the tablets in the mortar and pestle and all of that. The reason for that, again, is to prevent oxidation of Fe plus 2 to Fe plus 3 by oxygen in the air or oxygen in the water, and also to prevent hydrolysis. They also told you there the mass of each tablet was 0.325. So that's a whole tablet now. One whole tablet had a mass of 0.325, okay? So they made up their solution of iron tablet. They put that into the conical flask. So your iron tablet solution went in here, tablet solution went in there, and what they had in the burette then was the standardized KMNO4, okay? No indicator, remember? KMNO4 acts as its own indicator. So part B of that question, it says, why must the potassium permanganate solution be standardized? Well, it has to be previously standardized because it's not a primary standard, so we didn't know the concentration of it. We had to previously standardize it to get the concentration of the KMNO4. Why is it necessary to standardize the KMNO4 immediately before use? We said previously that KMNO4 decomposes in sunlight, so if you leave the KMNO4 sitting around in a flask, then its concentration will change. And what reagent is used to standardize KMNO4? Ammonium iron 2 sulfate. Okay. Now, when you then you're ready to start your titration, remember that you add a little bit of H2SO4 here too. This is your second time that you're using the H2SO4. It goes in here before the titration starts. Why? Same idea, to supply H plus ions to fully reduce the MnO4 to Mn plus 2. Now I've written the equation up here already, look. Now do you see the 4 oxygen atoms here? What's going to take those 4 oxygen atoms away? The H plus, and they have been supplied by the H2SO4 addition that you put into the conical flask before you started the titration, okay? Now the calculation then, stick with your steps. So your first step, number of moles. Now we're going to use our formula V by M all over 1,000. Now your starting point, you always start with a solution that you know the concentration of. So read the question. You've been told the concentration of the KMNO4. So we're getting number of moles of KMNO4 minus, okay? The volume, the average from the burette was 18.75. They told you the average. You didn't have to calculate that. Remember, if you are calculating average volumes, then you ignore the rough titration result and you get the average of the two that are within 0.1 of each other, okay? Now, when you work that out, you're getting 1 point by 10 to the minus 4 moles of the KMNO4. So you know the moles of KMNO4. Your next step then is the ratio. Now, from the balanced equation, the ratio of MnO4 to iron is 1:5. So you are going to need 5 times the number of moles of iron to completely react with all of the KMnO4, okay? So when you multiply this by 5, you're going to need 9,375 by 10 to the minus 4 moles of the iron solution. Okay? Now, our next step then is you equate the moles, 9.375 by 10 to the minus 4. So that's moles. You have to equate that to the volume that they use. They use 25 cubic centimetres. So divide by 25, multiply by 1,000, and then you're going to get moles per litre at moles in 1,000 cubic centimetres or moles per litre. Is that okay? Now, the next thing that they asked you to do then in the question, that you got the molarity of the iron solution, the total mass of iron. Now, don't get bogged down with the questions and be careful and read them properly and decipher what have you been asked. So in part 2 there of the calculation, you're asked for grams of iron, just iron, not iron sulfate, just iron in the 250 cubic centimetres of solution. Now, you know from the previous calculation that you have 0.375 moles in a litre. Moles in a litre. So you've two ways of doing this, okay? So what I'm going to do now is I'm going to change moles to grams. How do I change moles to grams? I have to multiply by the AR of iron. Now it is just iron that you're asked. So if I multiply by 56, I'm going to get, when I do that, I get 2.1 grams of iron in a litre. So now I'm in grams, but I want 250, so I'll divide by 4 and I get 25 grams of iron in 250 cubic centimetres of solution, okay? And that's your second answer, your second part 2 answer. Now sometimes they'll ask you for the mass of iron sulfate. If they do, then you'll have to multiply by 152, which is FeSO4. They didn't in this question, so don't be wasting your time. In part 3 then, they ask you to calculate the percentage by mass of iron in the tablets, okay? So when you're getting percentage mass, then you need the mass of iron in one tablet, and you're going to divide that by the mass of one whole tablet. Now, and multiply by 100 over 1, of course, to change to percentage. Now, they told me previously that one whole tablet had a mass of 0.325 grams, okay? I now know that in 250 cubic centimetres of solution, I have total mass of iron of 0.525 grams. But lads, in the question, they told me that they dissolved 5 tablets in the 250 cubic centimetres. So 0.525 grams is for 5 tablets. So divide that by 5 and you're going to get 0.105 grams of iron per tablet, okay? Because this is for 5, so I have to divide that by 5. And then when you do that and multiply by 100 over 1, you get 32.3% iron in each tablet. Okay, thank you.